everybody. Thank you for joining this seminar. My name is Marzia Dekani. I have the pleasure of introducing today's presenter, Dr. Alberto Meucci. Alberto is a senior research fellow at Melbourne University. He is also an adjunct research scientist at CSIRO. He has a background in civil and hydraulic engineering, having studied in Italy and Netherlands. In 2020, he completed a PhD in ocean engineering at Melbourne University and has since continued his research there. His research is focused on climate change impacts on wind waves, wind wave extremes, with an interest in spectral wave model representation of extratropical storms and their impacts on Australian coastlines. Please put your hands together for Dr. Alberto Meucci.
Thank you, Marzia, and very happy to be here today. And thanks for hosting me, actually. It's a pleasure to talk about what we've done at the University of Melbourne in the past few years about future projected wind wave extremes and what it's our understanding of the confidence around these parameters and what is the progress that has been there and what are the prospects of this research field, which is of interest for future extreme sea levels, which is one of the major concerns and research priorities here in Australia, especially. So, as Marzia also mentioned, I'm part of the University of Melbourne, and I'm a postdoc research fellow over there. But at the same time, I'm also working with the CSIRO in the Climate Research Centre in Aspendale as part of the ACS, which is the Australian Climate Service Airport. So today, I would like to talk about then wind wave extremes. So in general, wind waves and spectral wave modeling of wind waves, but with the focus on extremes, which has always been my interest. And we know that wind wave extremes, this is just a brief overview. You probably all know this, but they're important for coastal erosion and sediment transport. This is the first one, maybe a bit speculative, where people are in our group are also already studying this and trying to understand whether changes in wind wave extremes are actually impacting coastal erosion or not. But definitely they have an impact, storm waves, and they are having an impact on coastal erosion and sediment transport. Then they're important for extreme sea levels, as I've said, so for flooding and in combination with storm surge, and because they can amplify the height of the storm surge and breach coastal defenses, as well as they're important for the design of coastal structures and infrastructure, as well as navigation and maritime operations. And ultimately, they have an impact on, they have ecological impacts, but also they have quite a lot of interest. There is quite a lot of interest also for offshore structure. And in particular, one of the things that I found interesting recently working with CSIRO is that they have actually researched a bit what is the impact of wave setup. And they found a few years ago, they found that actually wave setup has a particularly important significant actually impact on the coast where there is a reef, which is one of the major actually in Australia. It's quite a lot of coastlines that are actually characterized by this kind of bathymetry, and so it's very important to understand what is the wave setup component to the extreme sea levels, and so to understand also how this is changing in the future, and so understanding how the wind waves extremes are changing in the future. So the first objective was during my PhD to try to determine the global significant wave height extreme value distributions, and to do that you can do it with looking at a number of data sets, and you have to look at long-term data set, or at least as long as you have available. And but now there are more than 30 years data set, and what we wanted to find is actually the 1 in any year return period value. This is because this is what it's usually sought by the engineer to design marine structures and infrastructure. And so we had a look, and what I'm going to present here. I'm going to present briefly some results of one of the PhD students that was there during my time as a PhD at the University of Melbourne, that she found extreme values distribution globally from multi-mission satellite altimeter, and then we're going to have a look at some reanalysis results, and then finally I'm going to present what are the what is actually my my main effort that was during the PhD, but also currently now trying to understand what are the changes in the wind wave extremes from climate models. So there are a few statistical approaches that we can to have a look at this, and the typical approach is to fit the PDF to the extremes with an extreme value analysis. And so the two major approaches are annual maxima and the peak over threshold. What I'm going to show here is an additional ensemble pooling technique that I've worked on with some colleagues at the Norwegian Meteorological Institute, and that we developed during my PhD to find direct return estimates. So it's just another statistical approach which actually allow us to find the extreme value, the one in any return period, without extrapolating from a PDF, without fitting a PDF to the data. And you'll see how. So the first, just briefly, the results of my colleague on the extreme value analysis determined from multi-mission satellite altimeter. This is the data set that was published by Ribal and Ian Young from the University of Melbourne, and this was the data set back then up to 2019. This is the same data set that you can find on AODN currently, but it's updated up until now, of course. And they, looking at this multi-mission satellite altimeter data set, they had a look and they tried to find, with a peak over threshold first and a generalized Pareto distribution fitted to it, they tried to find what are the extreme, the 100-year return period for the wind speed. And this is the results that they found from they go up to 40 meters per second. I want to maybe try to just remove this. Yeah. And so what you can see in here is the global distribution of the 100-year return period. You can see the signal of the tropical cyclones in here, and also some extratropical cyclones region in here. And you see that the most extreme climate for the wind is actually in the northern hemisphere. Extremes are also found in the southern hemisphere, but they're a little bit less intense than the northern hemisphere. So there is a little bit of an asymmetry in between the two hemispheres. And they did the same for the waves. In this case, for the waves, you see that the distribution is much more irregular. That's because of the nature of the waves itself. And then again here, the most extreme wave climate is in the northern hemisphere, North Atlantic and North Pacific, with waves going up to 20 meter for the 100-year return period, found from this, still from the peak over threshold generalized Pareto distribution approach, and slightly lower in the southern hemisphere and in the Southern Ocean. They also found, and I'm flying through these because I have a lot of additional stuff. This is a bit of an old work, but this is just to show you that they found the same distribution. This is just the same distribution with different color scale compared to ERA 5. You can see if I'm flipping through the two, it's pretty much similar what they found in spatial distribution of the extreme, or 100-year distribution. Just a little bit more of a signal in here for the tropical cyclone region, which is not really well reproduced anyway by ERA 5. But the scale of the data, it's more or less the same. And this is kind of expected because anyway, ERA 5 assimilates not all, but a few of these satellite data sets into the model itself. So it's a reanalysis, but we didn't know if these would translate also for the extremes, because actually the observation of the extremes are much less frequent. So in general, the spatial distribution is similar, and also the magnitude, they go up to 20 meter. And this is just to give you an overall overview of what are the values for the 100-year return period. We've added to these an ensemble pooling technique taken from operational forecast data set. I'm not going to go through the overall specific technical details of this, but the concept is that we are just taking ensemble forecasts at a lead times that it's enough in advance, so at day 9, from day 9 to day 10, so that these ensemble forecasts may be considered independent. There are 50 ensemble members every 12 hours that were produced back then in 2018, and we pulled the data set from day 9 to day 10. We just pulled the maximum of the lead times in between day 9 and day 10. And every 6 hours, no, not 12 hours, every 6 hours, we took the maximum every 12, and then we recreated a synthetic data set of up to 750 years, out of which we could actually estimate the 100-year return period directly in sample without fitting a distribution. And if you are more curious about what we've done, maybe we can discuss this later. But the concept is that we wanted to reduce the statistical uncertainty, which is just one of the uncertainties that you have into the picture of actually estimating these extreme values. And what we found, we actually wanted to understand, first of all, if this methodology gave us plausible results. So these are the results for the wind speed. As you can see, it's very similar, the spatial distribution. In here, you can actually also depict a little bit of the footprint of tropical cyclone. Here also in front of in the western side of Australia, but also the eastern side, and also in front of Madagascar. And these are the wind speed that they go up to 30 meters per second, the maximum in here of the 100-year return period for the wind speed. And this is what we found for the waves. So if you remember, the order of magnitude before was up to 20 meters. So with this analysis, we are actually having slightly smaller return values, up to 18 and 16. There could be a number of reasons for this. One could be actually the selection of the ensemble at advanced lead times could have actually washed away a little bit the extremes. And on the other side, these are also old cycles. So this is from cycle 36 to 41. And so these were the cycles that ECMWF was running back in 2016. And so since then, they may have improved also the representation of extremes in these models. So we did, in this case, reduce the statistical, the part of the statistical uncertainty, but there is still a lot to understand of what is actually the uncertainty inherent to the model representation of extremes, and then how we can compare to the observation and what are the uncertainties also of the observation themselves. So it's a bit more tricky than we think. So then we went on, and just this is after the work of my supervisor with Agostino Ribal on the satellite observation, and they found they calculated the trends for the significant wave height and the wind speed. This is the wind speed on the left column, and the significant wave height here. And these are for the top is for means, and this is the bottom is for the 90th percentile. So they went and computed the trends, and as you can see, there are. It's clear that. Computing the trends from multi-mission satellite altimeter from 1985 to 2018. These are centimeters per second per year of the wind, and it's clear that both the wind and then the waves, especially in the Southern Ocean, are increasing. So the climate is not stationary. You would say duh, but anyway, this is something that we needed to understand and to see if it was, the case. And so because of this, since the climate is not stationary, the idea was, okay, let's apply the ensemble approach now to understand what are the changes in the future. Because instead of selecting operational forecast ensemble members, we could actually select ensemble of global climate model driven wave model. So what I mean with that is that we are using now CMIP CMIP wind speed to force our global wave model from different recreating an ensemble of wave climate models. And so from this ensemble, actually, we could assume that these are independent and we could apply these. But the main thing, so how do we determine this impact? The main problem with these are that there are even additional uncertainties in climate projection, which originate mostly from the nature of variability, which is in the internal variability of the climate model. So how the oscillation, the interdecadal oscillation are playing, for example, a role into the change in the wave climate and how they are modulating the wave climate. On top of these, there is the modal uncertainty. So what is the modal response to the wind that we are forcing to it? And also at the end is the scenario uncertainty, which is actually external forcing, and it's which you can cover in a way running different scenarios for the future. Back then, they were the representative concentration pathways. Now we've run the new models with the shared socioeconomic pathways. So you can try to understand a little bit that just running different scenarios. But the idea was like, okay, we had this CSR ensemble already there from the CMIP5 phase, and we want to apply the approach, this ensemble pooling technique, to this 7-modal ensemble. And to do that, then these are the models that they were available. The WaveWatch 3 was run back then at 6 hour, and it's a 6-hourly data set, forced with CMIP5 global climate model. And these were the time slice available from 1975, 2005, the historical one, and 2081, 2100, the scenarios, the future scenarios, the future projections, and the RCP 4.5 and 8.5 were available. And these are part of this overall CowClip data set that was published in Nature Climate Change. These are just where these models are sitting in the clustering of the overall international global wave climate model community. And so what we did, then we had to kind of find a way to pull these extremes without any of the models actually overweighting the overall analysis. And so to do that, you would apply either a bias correction or a weighting technique, depending on the performance of each of the models. And in this case, what we decided to do is actually to use a standardized variable and just subtracting for each model the mean and then the standard deviations that we are pulling them all together, and then we are peaking. We are applying initially a peak over threshold, so we're selecting the threshold as the 90th percentile with a 48-hour storm independence back then. Now with the new analysis, we are even increasing these to 72 hours, but it's anyway guaranteeing already with 48 hours that the peaks of the storm are actually, that the peaks are coming from different storms. And then we select the 1,000 highest peaks. And with the same approach that we use for the operational forecast data set, now we have recreated a synthetic data set of 189 years for the historical part and 140 years for the future. That's because the difference in these values is because of the difference that was because the historical data set actually was up 26, 7 years in here, and this one was just 20 years. It's just, I don't know why, but they've run different, a different size of the for the historical one. This is just what actually how each model contributed globally and to the tail. So these are each model has a color in here. You pick we just pick the peaks over the threshold, and you see that this one is the 6-hourly HS and the tails of the data set without the bias correction, without the standardized set. And as you can see, one of the model, which is the Japanese one back then, which was particularly high, bias high, is overweighting in the number of peaks out of the 1,000 that we are getting. So that was like up to almost 400. When we are applying this standardized variable, actually, we are actually flattening this curve of the contribution of the model. So this was important to then finally apply our ensemble pooling technique. First, we wanted to understand if the spatial distribution was decently close to what we see from the CFSR winds. So the CFSR winds are a bit They are giving the wave watch 3 force with the CFSR winds is actually giving us quite high waves. So the comparison was not that fair in here because the CFSR winds are known to actually be overestimated and hence the waves. But the comparison was actually quite satisfactory because the spatial distribution and the magnitude is like up to 22 here. And the only thing we couldn't get was actually the tropical cyclones, but that's because here we are comparing a reanalysis where the signal of the tropical cyclones is clear and with very low resolution climate models where the tropical cyclones were not well represented back then. So now you see that with the new phases now, even the global climate model are actually increasing the resolution and they're starting to get even more of this signal in the tropical cyclone regions. But overall, the spatial distribution was kind of satisfactory if you don't consider the tropical cyclones region in the comparison with the reanalysis. And so we pulled them all together and we tried to find, if we can see a signal in the change of the wave height extremes. And this is what we found is that the signal was clear kind of, there was a signal of increase all around the Southern Ocean. That's similar to what you see, what already previous studies saw in the average significant wave height, but this found also a change in the extreme wave height, as well in the magnitude, comparing just the delta with the future projections minus the historical 100-year return period. So this is a delta of the 100-year return period for the high emission scenario, the RCP 8.5, and with changes that go up to from 6 to 10%, increasing in the Southern Ocean. We found also, we tried to find also if the frequency is changing, and apparently using the same threshold, the historical threshold, and applying that to the future one, we also found that there was also an increase in the frequency of the peaks that over the threshold, the historical threshold. And so still though, there was a bit of criticism that, discussing with my peers about this kind of approach, because mainly they were questioning how good is actually to rely on a single method and single wave model ensemble to actually find changes in the waves. And well, first of all, that's what we had available back then. And so we tried to kind of find a way, but the concept is that one of the main things was that you don't know what the wave model is telling you, and there is a lot of uncertainty in the wave model and how we are approaching this. But the idea was to find a signal of change and not be precise on the magnitude, because actually with the magnitude of the extremes, we don't even know. The uncertainties are so big, just looking at the historical climate from the analysis or observations. So what I believe is that there is still value in such approaches to kind of understand whether there is a signal and trying to make sense of what is going on and what is the signal that these models are giving us for the extremes, and if this compares actually with the signal that we find in the mean. And so the primary issue, though, back then was the accuracy of the wind speed and also the very low resolution of this wind speed, which they went from 250 kilometer and coarser. So on top of that, then we decided, okay, let's develop a new ensemble ourselves, because we needed it to run it for a regional wave climate model in Victoria. We needed the boundary conditions. So we said, okay, let's update the overall ensemble and develop this new CMIP6 derived wave climate ensemble with improved wave model physics as well, and a higher spatial resolution also of the wave model. And then we ran also continuous wave climate simulations. Two of these models out of the 8 model ensemble that I'll show you were run for 140 years. And that's because one of the questions was, okay, you are assuming in your approaches that the climate is stationary, but we should actually understand what is the modulation over the long term. And so there are also non-stationary approaches now, extreme value analysis, that we can apply to long-term data sets such as these 140 year. So we wanted to understand if the signal is similar and the spatial distribution of change is similar, also looking at a long-term continuous data set. And then finally, I'll show you a little bit of what, with the new models, what we found of what is actually the performance of the wave model. So most of the uncertainty actually lies into the global climate model wind speed when you're looking at the wave climate changes in extreme waves. But I wanted also, being me a wave modeler and also specialized on the wave side, I wanted to understand also what is the uncertainty that comes from the wave models, and other also groups from Europe also, they had a look at that. And so I'll show you a little bit of what is going on the wave model side, representing extremes, and what it means to change the wave physics to the final results of the extremes and the magnitude of the extremes. So this is the new, this is just a Gantt chart of the new CMIP6 wave climate runs. They are currently under review. These are scientific data. The review was positive. So this will come out very soon, and it's being used already for wave power analysis. But that's the two models. So what you see in here is an acronym. WW3 means Wave Watch 3, which is the model we are using for the waves, and FORCE with the Access Model 2 in here. Just some acronyms for the various models. This is Access Model 2, ECR 3, the German model, the CMCC, the Italian model, French model, and so on. This is the Korean model and the two Japanese model that we used for our ensemble. The selection of the criteria were mostly three. First of all, we wanted 3 hourly wind speed this time, because back then when we ran the first result that I showed you were done on 6 hourly data. So we wanted to increase the resolution, the temporal resolution, to pick more extremes, of course, because ideally you would go down to 1 hour. But for climate models, because we had to run a full ensemble, we had to also stick to what we had available from the global climate models community. Some people are asking to the global climate model community for the CMIP7 version also 1 hourly wind speed, but we'll see if they're gonna be available, because it's quite a the storage is already, like a lot of models have been produced, and the storage is quite big for this data set. And also the second criteria was the performance of each global climate model 10-meter surface wind speed. We measured this with an M-score analysis, an M-scale score analysis against ERA 5, and we picked best one comparing with ERA 5, and finally the alignment with the Australian Climate Service GCM selections. At the end, we just aligned on 2 of these, but that's because we also needed the 3 hourly wind speed, and we didn't go. So these criteria were kind of mixed together, and we couldn't get a full overlap with what the Australian Climate Service actually chose, because that was based on rainfall mostly, and mid-sea level pressure, and also surface temperature. So for rainfall and analysis. So this is the model that we've run. Just briefly, this is the grid that I've run. This is just a 3-grid approach, irregular grid, just a regular grid from 55 south to 55 north, and 2 curvilinear grid to model the poles. The ST6 parameterization has been used. This is the source term physics. I'll explain a little bit more about what this means for the wave model side. Discrete interaction approximation is for the nonlinear interaction, but we'll get to it a little bit later, maybe for who's not an expert on this. But mainly the model outputs now are 3 hour and now at a 0.5 degree regular grid globally. So we could increase by 4 the resolution of this wave model. The one that we used before, they were up to 1 degree only. And spectral resolution as well, because we outputted also the wave directional spectra. So these are the results of the overall ensemble average no weighting, no bias correction. This is just a modal democracy approach, just looking at the differences of the ensemble average, the 8 modal ensemble average for the average wave climate, significant wave height, against satellites. This is from 1992 to 2014. The model, the CMIP6 model, the global climate model, go up to 2014. That's why we stopped there. And this is the comparison with ERA5 hindcast. So the ERA5 hindcast is just another version of ERA5, but without wave height assimilation and with updated wave physics, which are much more similar to what we are running. So that's why we could compare better our models. The only thing I wanted to point out in here is just look at this kind of behavior in here that you don't see, for example, in here. That's because here we are comparing with satellites, and so we are comparing with real observation of the sea state. Here we're comparing with the model, and so the models, this tells us that the models, they have a problem with the directional spreading when they are approaching the island. So behind the island, what is going on is that the model is not capable to transfer the energy, to diffract energy around the island. But a signal, it's found both in the satellite comparison and the ERA5 comparison, which is this blob, red blob, south of Australia. And this tells us that probably the overall global climate models, they are struggling to get something in here, and they have probably too high wind speed in this region compared to what actually we see in the historical period. And so this is something to keep in mind. And actually the comparison with both observation and models, they tell us, different aspects of how these models are actually performing. Here, we just wanted to understand whether we have improved with our ensemble, with what we used before for our ensemble pooling technique. And the M skill score we used in this case is just similar to a mean square error over the variance, over each direction, X and Y direction, and it's computed by each region in here. These are regions that we selected based on what in the wave model community are using since 2003, 2002, but we also computed these for the IPCC new climatic regions. But this is just to show that our CMIP6 ensemble is actually outperforming. This is the orange one, because the higher is the value, the better is actually the comparison with ERA5H, the model, and is outperforming in every region the previous wave climate ensemble. And so this is actually something nice and which is positive. And so we also wanted to understand what is the relative performance of each model of the ensemble compared to each other. This is what you see in here. This is a portrait plot. This is a very well-known plot in the climate community and was also in the IPCC report 5. And what you see in here is that just the median, the RMSE over the median RMSE over the 8 model for the significant wave height, 90th percentile significant wave height, mean period, mean direction, and wave power. So the one that they have a negative value, so the blue ones, it means that their RMSE is lower than the median of the ensemble. And so it means that those models are actually better performing than the rest of the ensemble. And so in here, you could actually find that the Access Model 2 and the ECR3 are the 2 best performing ones. And so these are the ones we run for the 140 years continuously. These are additionally some tailored plots that show how the model compared to the satellites in here. This is a comparison with the satellites. So the satellites are sitting in here. This is the black star, and this the square, the black square is ERA5H, and these are the models. And as you can see, the models are all sitting in here because in this approach, I've used monthly means to find the correlation and the RMSE. However, I'm now modifying this because we also received this in the review that for climate models, and we knew that, but I wanted to actually show the difference with the reanalysis and the climate model. But for the climate model, you can't really take monthly means and compare them with the reanalysis. You have to take actually the climatological mean and compare them with the reanalysis and do the RMSE over a spatial distribution, because the climate model are not in phase with actually what really happens and what we observe with the satellite and also the models. And that's why the correlation is lower and also than the ERA5H in here. So when I'm doing now the new analysis and all of these models, when you're looking just at the climatological mean and just finding the RMSE spatially, and also over 12 months, you see that all of these models are actually clustering together, which is actually good. The climate model clustering with the ERA5H, because it means that the climate is actually well represented, even if it's not in phase, it's actually well represented and comparable with what a reference reanalysis tells us. So these then are just some of these are the anomalies found, 10-year running mean anomalies found for the two wave climate model that we run for 140 years, divided by the IPCC assessment report 6 regions. You can definitely see that in the Southern Ocean, again, we see the signal of increase for all the models, and also for especially for the scenarios of here I'm showing, it's a bit small, but I'm showing both the SSP 1 to 6 and the SSP 5 at 5 scenario. And we also find the same behavior, and of course a little bit more of fluctuation is in here, but for the 99th percentile. So you can actually see that also the extremes are changing in the Southern Ocean, slightly decreasing in South Indian Ocean. And in the Arctic Ocean, we have this signal. That's because of how these climate models are representing the sea ice concentration, which is a completely different problem, because these models cannot really represent well the sea ice concentration. So the changes in there are mostly dominated by these sea ice retreat. This is just a comparison of the new models with the spread of the full CalClip ensemble, the one published on Nature Climate Change. This is the average, the black one, where it sits, and these are the new models where they are telling us that the climate is going. But we saw this fluctuation, and so we just wanted to have a look briefly how this compares with the SEM. And as you can see here, these are in a dashed line is the SEM index for 140 years, and the two models. So the SEM index can be computed for each global climate model, of course. And if you detrend these, you can actually clearly see that both for the mean and the 99th percentile, the fluctuations are following the SEM index for the Southern Ocean. So we're looking at this climatic region here, the 57. So that tells us that part of the change that we are seeing also at the extremes, it's given by the fluctuation also of something like the SEM, or the Southern Ocean Oscillation, as you want to call it. But in any case, applying a non-stationary EVA, we found that the signal for the access model, applying a non-stationary EVA to 140 years from the access model and ECR3, it's similar to kind of like spatial distribution. You could see some of the signals in here for the trade winds area, the southern hemisphere. We could actually see that still this signal is there, even applying a non-stationary approach to 140 years compared to the previous ensemble pooling approach. So we found consistency in these results, at least, maybe not much for the northern hemisphere, but in general, the signal is similar somehow. It's not really comparable though in the magnitude, because you're looking at percentage changes in here, and here are centimeter per decade over 140 years. So we are now I'm now moving on with my analysis and just selecting the peak over threshold. This is just an example for Rottnest Island, how I select the threshold and then the directions, for example, in here, connected to the HS that is exceeding the 99th percentile threshold, because what I want to know is just first I want to select based on the energy, what are the most extreme sea states, and then what are the changes in the peak period and the peak direction. So in the extremes, peak period is changing, and it's for the Southern Ocean. It's not clear if the direction is changing for the extremes as much as what we see from the mean peak direction, which is here. As you can see, this counterclockwise change due to the moving of the westerly south. And so this well, and that coming to Australia tilted a little bit to the north in the future. So then I have to do more research on this and actually apply all of these analyses to all of the ensemble members, and then trying to understand whether the changes, there are significant changes in the direction for the extremes. In addition to this, I don't have much time left, but I also had a look at extratropical cyclones and how they perform and how the wave models are performing over there. This is just a work we've done and we've published in JGR Ocean, where we had a look at the April 2021 storm, which actually swept up these to 30 meters from the seawall, these huge rocks. So it was kind of a major event that impacted Victoria in here, in this region, so where the red is. We had a look at the wave model. This is the wave model and how the source term, that is what I was talking about before, the ST6, is actually performing for these three main elements, which are the wind speed, the wind input, the nonlinear interactions, and the dissipation. These are the main input that we put in the wave model, and that they drive the offshore performance of the wave model. So what we found practically comparing the different models is that none of these models, this is just walking along the storm and comparing with the measurement of a satellite. The satellite went up to 17.39 meter, and we found that none of these models, they even reached like 15 meter in the Southern Ocean. And so we are far off, at least in this case, with the Southern Ocean. And ERA 5 here, which is assimilating the wave data, actually tries to, insert a little bit of energy, but it quickly disperses this energy here down, moving along the track of the storm. So in this case, also wave data simulation didn't help. And that's the reason why we found, we measured actually higher waves at the impact on the coast there in Cape Bridgewater and Cape Sorel than what actually was modeled by ERA 5. I won't take you much through this. This is more of technical details of why this happens. But so we through the work we've done with ACS and CSIRO, we have updated the model. We've tried to actually see if we can actually better capture these extremes. And this is done through a wind correction. So we are correcting the wind before inputting in the model. And through this wind correction, we could actually, because there is an underestimation of the wind speed in the ERA 5, correcting the wind, we could actually, we want to see if actually the wave model gives us more plausible results, and if we can get closer to what we see from the observation for the extremes. On top of that, there was a problem with the negative wind input and other aspects of the wave model. We had to kind of rebalance everything. I won't take you much through this, but we've done a bit of work on the dissipation and how the dissipation of the swell is impacted by the negative wind input. And so reducing the negative wind input term on the waves, we are actually getting better results also in the swell dominated region of the Pacific. And so we worked on this and all of this tuning with the Bureau of Meteorology. And we came up then with the results for the ST6 as it was, and how I used it in the wave climate models, a better updated version, and a version of the ST4 that is another complete package different to what we used, that is used at the European level and in the US for wave watch. And again, you can see in here, these are collocations run against satellite. And in this case, we are actually picking the right value at each 12.5 kilometer grid cell, which is the resolution of this model, which is a high resolution. And as you can see, this is the curve. And the model that we are running is actually not picking the extremes. And these are the blue and the light blue and the dark blue are the satellites with two different calibrations. The red is actually the ST4, We don't really know what the ST4 does. It seems like it's picking the extremes well, but then it's actually overcooking all of the rest of the bulk of the data, as you can see also from the PDF in here. So now we actually got a better results for these ST6, but still there is an issue over there that we're trying to solve later on in the future. But in general, the overall performance, as you can see, even if the extremes, it seems like we are getting better extremes in here. This ST4, which is the red one in here, is actually overcooking the whole comparison with the globe in comparison to the ST6, which is the one run operationally also now. This version here is the one run operationally with the OS wave at the Bureau. This is just the consistency of these. I just wanted to show you, this is the problem we found also with the extremes, also regionally in Victoria. And it doesn't seem to be the same actually for Western Australia, because again, now the curve you see in here that the blue and the two blue lines are actually sitting very well with the gray line, which is the one that we chose and that the Bureau is running for the new wave hindcast. And the rest of the data is actually overcooking it. You know, the ST4 and the other model are actually overcooking the extreme. So for Western Australia, this doesn't seem to be a problem. So now we're trying to understand regionally how all these models are comparing and how the extremes are comparing. This is just the evaluation comparison with the Western Australia and the Southeast Australia climate for the various months. I'm just going to fly through it because I don't have time. But in general, what I wanted to conclude with, and sorry if it was a lot of inputs, but I hope I managed to kind of convey the message. But in general, we found that global data set from reanalysis models and altimeter observations, they give us consistent results for global 100-year HS, which is good. We reduced the statistical uncertainties with ensemble approaches. We found that over the last 30 years, there were small increases across the Southern Hemisphere, but also the projections show an increase between 5 to 15% is the Southern Ocean. This is with the high emission scenario. This is consistent with what we found so far with two models with a non-stationary approach over 140 years. But there is still like a lot of uncertainty in extreme wave direction, whether this is changing, whether this will impact the coastal this will impact coastal erosion or erosion patterns. We have uncertainties, future projected changes also in polar regions. I haven't talked about it, but that's one of the things we are trying to understand. But at the same time, we saw that the CMIP 6-8 model ensemble improves over the previous generation one. And after that, what we are focusing now on is actually to improve the wave model in the reproduction of the extreme and try to see with the next coming wave climate analysis if we can study a better wind stress capping, which is the problem why you see this cutoff in the extremes. But in general, the enhanced wave model calibration with this called P72, which is the one that I showed you before that the Bureau is running, shows improved performance under extreme conditions. So that's actually pretty good, and that's what we're planning to go on for the Australian Climate Service Airport. So in general, these are the prospects for the wave climate extremes and also wave extremes in the future, and what the research actually I think should focus on. And mainly, we found that the CMIP 6 actually showed improved performance, and so now we have available also high resolution global climate model. And in the future CMIP 7 phase, we will have even higher resolution wind speed to compare with, but we also have Cordex Australasian downscaling efforts that we can use, and we will use with CSIRO to run new models with high resolution wind speed. There is improvement we could do on the physics side of the story, improving the drag coefficient formula. I didn't talk to you much about that, but I can, if you have any questions, I can answer to it. And then the CalClip community, which is the coordinated wave climate project globally, is also focusing on a synthesis effort now on the CMIP 6 and IRS-MIP driven models, wave models, that will be available probably in a year's time. And so we'll have even a better picture of what is going on to the waves and the extremes. And finally, the ACS products with which I'm working on with CSIRO will probably supersede and will actually be much better in performance and supersede what was the already successful Cochlear analysis and Cochlear Imecast. So that's it. Sorry, I took a bit too much.
Thanks, Alberto. Very interesting presentation. Do you have any questions from the audience in the room or online?
You might want to just flip on so you can see the...
I'm not sure how I should do that, but I'll try.
So even when I really flew very fast through everything we've done, but even just clarifications are more than welcome. I mean, I could have managed to bring everything probably together without.
So if you have any questions online, please raise your hand or, okay, we have two, I guess. Jason, please.
Hi, Alberto. Jason McConaughey from Shell, Principal Technical Expert from NetOcean. Thanks for the presentation. I had two questions, maybe to get your take on. You used the DIA for your modelling of the storm in the Southern Ocean. What is the reason you do not use the MDIA, which we know should produce better results, particularly for spreading?
So what I wanted to do there, yes, that's true. So what I wanted to do in there is use the common approach that has been used within the wave climate community to run the models and to understand how these performs and mostly isolate the performance of two different physics. I haven't showed the difference in the analysis, but my objective in there was not to get the right magnitude of it, but more showing how the two models are performing in between each other and how they are distributing the wave energy across the frequency spectrum, which is something that I haven't shown, but it's what we published with the JGR Oceans paper. So that's why I've used that approach, because that was commonly used in the wave climate community and what's run.
Okay, I guess that's the answer is the same for my second question. Is that why aren't you using the ocean currents? Which will cause quite some change in the swells in the Southern Ocean.
So the ocean climate, so the ocean currents, there is an approach that you could use for the wave watch, but it's kind of a very crude approach. The optimal way would be to have a coupled wave ocean model, and that would give you much better differences. But what it was found with just the crude approach of Wave Watch 3, at least for the average condition, is just a change of 20 to 30 centimeters in the average condition for the climate in the Southern Ocean, but not much more in the signal. But that's true. That's for extreme. It's definitely important, and that's something that we are thinking about for future wave climate model to actually couple them with the oceans and also the atmosphere, which is completely different also kind of effort, especially when you're running, you need to run an ensemble of model to cover the overall uncertainty of this climate model.
Thanks once again.
So I guess Paul online also had question?
Yeah, thanks very much. Very interesting talk. I've got a couple of questions. The first is, my understanding is that the transformation from wind to wave, the standard models over-predict that in very, very severe storms, which is for very, very high wind speeds, which is the case, I guess, where engineers are interested for design. Is that included? Is that overestimate included? I mean, you're upping your winds, but should you be upping the waves if the most extreme winds are not driving as much energy into the wave field as expected?
So you're saying that there is a projections in the wind that you know about, that it's gonna increase significantly in the extremes, and you're asking if we see the same signal in the waves?
Well, I'm asking whether the wave model, the wind to wave transformation input that you've used,
Yes.
is taking into account the fact that very, very steep, very, very fast winds don't put as much energy in as was expected.
No, it's not. But because you would need to properly account for it, you would need a couple approach with the atmosphere. That's what it's used by ECMWF, and that's what they run. But this wave climate model, because they are done singularly by research scientists like me or like, and they've been all run uncoupled. And so this is not really what has been done so far. But that would be actually my, I would like actually to implement that in the future. And I'm trying to understand how I could actually run an ensemble of coupled wave models. And but definitely, yes. Yeah, I mean, we've collaborated with, for example, for the extratropical cyclone analysis, we've collaborated with the ECMWF, and we had a look at their also new results from ERA 6, and definitely that's one of the things that they are implementing much better now in their model, and it shows that the wind, after a certain point, it's not inputting much energy anymore to the waves. But,
okay, that's interesting. So we'll ask you back in a year's time to tell us what this effect is. The second question was one more related to large-scale geophysics. That, I mean, you're running a wind wave model, but the waves are significantly correlated with things like ENSO, El Nino in the Pacific, the NAO, and the local patterns in the northeastern Atlantic, and sea surface temperature in the Pacific as well. And these have decadal or multi-decadal timescales. So you're looking at blocks of 30 years up to 100 years. Are the changes you're seeing, at least potentially, due to the large-scale background geophysical changes rather than climate change?
Yeah, there is a component to it that I've shown, I believe, in one of the slides. I just probably flew through it very fast, but if we cannot get it on, it's okay, Marzi, but maybe just put the full presentation. There is a component to it, and we've just had a look so far at the SAM, which is interest region, and there is an impact of that, of those oscillation here, of those oscillation, the decadal oscillations on the wave climate. And this, what you're looking at here, these are anomalies of the wave climate. But so if you trend the overall thing, then definitely you can see that the oscillation of the mean in the bottom left figure of the mean HS it's connected to the dashed line. So the blue continuous line with the dashed line of the semi, and then the red continuous line with the dashed red line of the semi for the two different models. But still, as you can see from the not the trended scale, I believe the change when you're looking at 30 years, it could be, if you're just comparing two 30-year slices, then yes, it could have a big impact. But overall, the overall like 140 years, as you can see from the line with the trend, I think still a signal. It's kind of clear, in my opinion, and it supersedes what we see from the oscillations, the impact of the oscillations. At least for the Southern Ocean. For the rest of the globe, I haven't had a look at it myself because you need to have a look at much more indexes. But yeah.
Yeah, I mean that's really what I was coming to, that the Southern Ocean and out in the middle of the North Atlantic, maybe it's just one cycle that matters to you, but elsewhere, particularly in the North Pacific, it's very much more complicated.
Yeah. So we had one of the students at UniMelb had a look at the modulation of wave climate historically, and but we didn't have a look yet at future projections.
Okay, very interesting. Thanks very much.